Alright, so the idea here is I'm given an exponent module and I'm trying to find the answer of that exponent module. But how does it actually work? The idea is I'm given a number x and I'm asked to raise it to the e. Before I do this, I'm going to take x and I'm going to split it into two components, right? The first component is going to be z ln of 2. And the second component is going to be the residual. What the fuck am I doing? All I'm saying is x is going to be ln 2. So ln 2, like ln e of 2 is just some small ass number, right? It's probably like e to the, I don't know, 0.7 or something. I don't know, right? But it's some number. This is a constant. And if I take some number and I multiply it by some other constant called z, and I add some residual to them, I can get x, right? And this is intuitive, right? All I'm saying is x equals some number multiplied by some number plus some number. And if I can change a and b and c, I can definitely make this true, right? Well, not a is ln e of 2. If I can change b and c, then I can definitely represent x, right? I can scale ln e of 2 to some number and then add some whatever's left to get it. So like if x is 4, and for the sake of just, math, we say e equals 2, so ln e of 2 is just 1. So if I say 4 equals 1z plus r, then you can easily say that, oh, let's just let z equals, 3 and r equals 1, and then it will work. Or z equals 4 and r equals 0, and it would still work, right? So you have all of these options to play around. Okay, so we've agreed that e to the x is going to be e to the z ln 2 times r. Sorry, plus r. Right? As proven here. And then we agree also that e z ln 2 times e to the r is what this is equal to. So e to the x can be broken up into e z ln 2 times e to the r. Okay. And then we've agreed, or we know, that e z ln e of 2, like all I'm saying is e raised to the thing, which when e is raised to gives me 2, raised to z. Like this is just me saying, like e ln e2 raised to z, and e ln e2, e raised to the thing that makes it 2, means that it's 2 to the z, right? So e to the x is equal to 2z e to the r. Okay, we're very solid, we're getting there. Now, 2 to the z is nothing but shifting e to the r z bits. So e to the x is really just e to the r shifted left by z. Okay, and so, but like what is z? Well, what we do is we just say, okay, let's take x and let's divide it by ln e of 2. And then that's going to equal to z, right? And then so like I'm just saying if x is like 10, and again, for the sake of engineering, ln e of 2, assuming that e is equal to 2, is just going to be 1. And so 10 divided by, let's call this 11. And so 11 divided by 2, let's say, so okay. X, for the sake of example, is equal to 11. And e, for the sake of this example, is equal to 2. And so ln e of 2, for the sake of this example, is equal to 1. And x is equal to ln e of 2 z plus r. To find z, I'm going to say x divided by ln e of 2 is equal to, in this case, 11 over 2, which is going to round down to 5. So x is equal to 5. And then to find r, I'm just going to say, well, z is equal to x over ln e of 2, which is equal to 11 over 2, which is equal to 5. And so x is just equal to whatever ln e of 2 times, r is equal to times z. So x minus that, right? So x minus this gives me r. And so r is equal to 11 minus 5 times 2. And so r is equal to 11 minus 10. And so r is equal to 1. So I say 5 ln e of 2 plus 1 is my x. And in that case, e to the x can be represented as e to the 1 bit shifted left 5 times. E to the 1 bit shifted left 5 times, right? And what is e to the 1? Well, I know by the Taylor series, it's just 1 plus x over 1 factorial plus x squared over 2 factorial, and I can ignore the rest because this is a very small number. And it's just 1 plus 1 over 1 plus 1 over 2, and so it's just... Damn, bro. I can't do math. 1 plus 2 plus half, 3.5. And this sucks because it should be 2.7 something, right? But yeah, I might have done a mistake somewhere. 1 plus x squared. Okay, I don't know. Doesn't matter. But basically, you can approximate that part away by Taylor polynomial up to the second degree. Taylor polynomial to give you e to the whatever bullshit that's left over. Fair enough. And so that's all this code is doing. All we're saying is, z is equal to x divided by ln 2 inverse is just 1 over ln 2, ln e of 2. And we're saying multiply that by x, qn is x, right? And so x divided by ln e of 2, by what we just said here, x divided by ln e of 2 is how I find z. And then we do this weird thing with fpmol bit shifted fp bits. This is a little bit, I don't fully understand this. I think this is just like a result of the fact that we have to, yeah, like we just want an integer number. And so if x divided by ln of 2 was to give me like 5.4, then I just want 5. And so I shift, like this shift somehow gets rid of that 4 and shifts everything to 5. Okay, we're just gonna go with that. And then QP is our residual, is our R. And so QP is just going to be R is equal to, as we said earlier, x minus z ln 2, because that, you know, x is equal to R plus z ln 2 because we found that. And so I find my R, and then my approximation for R is going to be, you know, because it's e to the R, right? So e to the R is going to be 1 plus R squared, 1 plus R squared over 2, or something like that, right? It's basically a quadratic formula. It's basically quadratic, right? So yeah, we get QP plus QB times, like this is just saying R squared plus BR plus C. So R squared plus BR plus C, where QB and QC are just parameters that we fine-tuned that are very good at approximating the Taylor series, the Taylor series of the exponent. And then the output Q is going to be, like as we said, right, e to the x is going to be this 2 to the z e to the r. And so I found e to the r, it's just ql, and 2 to the z times e to the r is just e to the r shifted left z bits. And that's what we do here. We shift it left, and then boom, we're done.